So what we will do next is we will look at a simple, very simple antenna which is called a Hertz dipole, where this J term is extremely simple. Okay. So it will just give us practice in this flow of derivations. Okay. Then later on we will come to a little more interesting problem, that if I give you, so what is this Hertz dipole that I am talking about? It is an antenna of very small dimension, very tiny dimension. So the current over it is not a function of space, it is just some value. So that is why I can do step 1, 2, 3 easily. When I go to real life problems, I actually do not know what is the current on the antenna itself. So I have to solve and find out the current first, then repeat these. So there is a step 0 added over there, and that is where computational EM helps us. Okay. So we will have a look at this, the simplest antenna, which is your Hertz dipole. Okay. Okay, so let us look back at our definition of A over here, right. This is our definition of A. Okay. So now what is a Hertz dipole? As I have already indicated, let us say this is my coordinate system and I put one tiny piece of wire over here, okay, very tiny and of dimension delta z, and because it is so tiny I can say that the current in there is constant, need not be a function of space. So the J x y z, I can ask what is this current as a function of x, y, z. So what can we call it? How will we write it? I have to write it as a function of x, y, z. So be a little bit more precise in how I write the current. Has to be, there have to be delta functions because it is very small, right. So what about the x dependence of this? Delta, there is going to be a delta x, then delta y. Okay, so it will not be a delta z because then it will be a point source, it will not be a line current, right. So this will be some constant I and along z cap, okay, for delta z by 2 okay, and 0 else. So it is like a tiny little step function. Okay, so it's to drive home the point that it's very thin, infinitely thin, and having some finite dimension only in one direction. Okay. Now since this is a 3D problem, I need the 3D Green's function. So what was my Green's function in 3D? If you remember, e to the minus jkr by, was it r? Well, r minus r, I am just writing this as r, okay, fine. So I will write it as r prime. So then this becomes r minus r prime, there is a mod r minus r prime. There is one small thing you are forgetting, there is a 4 pi, the normalization factor was 4 pi. Okay, this is for the outgoing wave that we have. Okay. Okay. So from here I can write down A for this Hertz dipole. It is going to be, we have written it as the convolution of J and G3D. Okay. Now of these, when this convolution will have 3 integrals, x, y, z, x, y will pop out, right, I will only be left with z, right. So this will become, so let us write it as mu. So direction is going to be z hat because j is along z hat, then I have a mu which was always there, and then I have an integral over minus delta z by 2 because that is where the current is 0, I mean non-zero, and then the I term which is constant, e to the minus j k r, right. So we can call this guy as r, right, 4 pi r dr prime, right. R is some general point over here, okay, and this is dr prime. No, the problem if I write it as simply I naught z cap is that when I go into this definition of A, when I do the integration, what will I integrate over x and y? If I do not have the delta functions, I will have the integral over the entire space, but I know J is only confined to a small volume. So, how do I quantify that? Either you give it some finite radius, then this integral becomes complicated, but I want to say that it is a one dimensional current. How do I do it? I have to put in the delta function over there. Okay. So, what would be a reasonable way to simplify this term? Remember, this delta z is very, very small. That's what makes it a Hertz dipole. What approximation can I make over here? Remember, r over here is mod r minus r prime. X minus Taylor approximation, something even simpler than that. So, what is r prime? R prime is some point over here and r is over here. So, you are looking at this distance, all of these distances in this convolution. Make it approximate. R prime is generally going to be very small compared to r, right. So, I can assume that this is constant. So, I can just pull this out over here. So, it will become z hat mu I delta z only will come out and e to the minus j k r small r. So, when I write small r, it means the distance, okay. I am not putting the mod underneath it, divided by 4 pi r, okay. So, we got all our constants over here. Yeah, I think it's all correct. I will just write one thing over here where r is equal to mod r. So, the next thing that I have to do is find out, if I look back over here at the steps, do I have my j now? I mean, I had my j, I had my g, I calculated a. Next step would be to calculate h, right. So, for h, what is the relation I use? 1 by mu curl of a, right. So, we can call this as step 1 and this is step 2, 1 by mu curl of a, okay. Now, you should use your coordinate system to your advantage. There are sort of simple ways of doing this and there are some very complicated ways of doing this, and even in the literature you will find complicated and simple ways. So, we will take one elegant way of doing this. So, curl of a, now what is the coordinate system in which you would want to do this? Spherical is what you would want to do this in, right. You could also write this as r as square root x square plus y square plus z square and do it in Cartesian, and that would be a lot more work, okay. So, let us before we actually take the curl, let us do some simple sort of things over here. So, a is 1 by mu curl of a z hat, okay. Now, this a, I am taking curl of two quantities over here. So, there is a simple relation in vector calculus, it is like a product rule, right. I can use this product rule over here and write this as, so the first term is going to be equal to, I have del of a z cross z hat, okay, plus a z curl of z hat, okay. This is a vector calculus identity. So, what about, so this is just like your product rule. What happens to the second term now? What about, can you say anything about this term? Curl of h hat, what is it? Curl of a constant vector, what is curl of a constant vector? 0, because what does curl have? Del by del x, del by del y, del by del z of anything but constant. What is z hat? 1 times z hat. So, this guy goes to 0. So, I am only left with 1 by mu del a z cross a, across z hat. So, notice just by this simple modification, instead of having to take a curl in spherical coordinates, what do I have to actually take? Just the divergence. Divergence is much easier to calculate, right, than curl. Sorry, gradient, not divergence. Gradient is much easier to calculate than curl, right. So let's see how that works out. Now, also this is the gradient in spherical coordinates, right. So let's write that down. So h is equal to 1 by mu. Okay. Now gradient will have what all terms? R hat, theta hat, phi hat, right. But Az is a function of what? Only a function of r. So the gradient is simply del by del r hat, only one term will be there. Okay. So let's keep our expression of A's over here. So let's write down all the constants. So this mu is going to get cancelled off. So I'll have a I delta z by 4 pi, I delta z by 4 pi, that's the constant part. Then I have a del of, del by del r of e to the minus j k r by r hat cross z hat, right. And that's very easy for me to do. I don't even need to remember the form of the gradient in spherical coordinates, which is not very easy to remember. So what does that give me? So I delta z by 4 pi. This is an easy thing to differentiate. So first term will give me a minus jk e to the minus jk r, actually e to the will come out common, so let me leave it over here, divided by r, then minus 1 by r squared e to the minus jk r cross z, right, product rule. So this is my coordinate system. Now what is being asked over here? R cross z. What is r cross z in spherical coordinates? Wherever r is, take r cross z, what will I get? So theta is which direction? This is theta. So it will be r sine, right, cross product, and direction more importantly. You have what are the spherical coordinates? R hat, theta hat, phi hat, right. So which way is your theta hat? So this is what direction? R hat. What way is theta hat? Downwards. Which way is the third direction is? Phi. Is into the board or out of the board? Into the board, right. So this is my phi hat. So r cross z, where will it always point? R cross z, where will it always point? Minus phi hat, no? R cross z, and magnitude is sine theta, right. So this minus, so r cross z, this will become minus sine theta phi hat. Okay. So this magnetic field becomes I delta z by 4 pi jkr plus 1 by r square e to the minus jkr sine theta phi hat. So the reason that we got, did we have to do much effort to get this? No, right. And the reason is because we made these intelligent choices. Here I didn't go about, all gung ho trying to put in the curl in the spherical coordinates, right. I would have to do lot more algebra. This is 0. Curl of a constant Az is not 0. Okay. So, for example, if you look at the way Balanis does it, he takes a few more steps because he is doing it in a not in the smartest coordinate system, but the other author for this is Stutzman, is the other book. He does it in this nice way. So, that just by geometry you can see that this h is always pointing in the phi hat direction. Okay. So, once I have got h, I am done. I can get my electric field how? By taking curl, right. So, I can get E from here by simply the curl relation, right. So, it will be a curl of h and 1 by j omega epsilon, okay, away from source. Anyway, my source is a delta function, right. Okay. So, this we will complete this derivation in the subsequent module. Okay. So, just one last thing I would like to draw your attention to is that there are two different parts of this magnetic field. One has a 1 by r dependence and the other has a 1 by r square dependence. If I go very far away from the object, what term will dominate? Only 1 by r will dominate, 1 by r square dies away, right. So, the same actually, without yet deriving it, I can tell you that the same will happen for the electric field also. The field far away from the dipole will be dominated by a 1 by r term. So, does that contrast with something that you have all learned from like class 9? R cube. If I take a point charge, what is the electric field far at any distance away from it? Coulomb's law tells me 1 by r square. R cube. For a dipole, right? Yeah, for a dipole it was 1 by r cube. For a point charge it was 1 by r square, right. But here what do we see? Electromagnetic fields 1 by r far away from the sort of the smallest building block of an antenna, which is a Hertz dipole, gives me a 1 by r. Okay. So, that is if you do jk, okay, alright. So, far away fields are of the form 1 by r. Okay. This will be important as we go ahead, and this is true for any antenna, any weird shaped antenna. Go far away from it, the fields are going to fall off as 1 by r.